the morning of June 30, 1908, the sky over central Siberia appeared to split in two. Eyewitnesses described a second sun crossing the horizon, followed by a blinding flash and a sequence of detonations so powerful they threw witnesses across rooms at a trading station 60 kilometers away. The event flattened 80 million trees across 2,150 square kilometers of remote taiga. To put that scale in perspective, the energy released was roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Russian mineralogist Leonid Kulik dedicated his career to finding the source of this destruction. In 1927, he led the first of 4 expeditions into the region, navigating frozen bogs and dense insect swarms to reach the isolated coordinates decades after the blast. Based on the eyewitness reports and the massive radius of the dead forest, Kulik had a clear scientific expectation. An impact of this magnitude had to leave a significant physical scar on the planet. Kulik assumed that at the center of the devastation, he would find a massive iron meteorite at the bottom of a deep impact crater. Instead, he found miles of pine trees knocked flat in a uniform, outward-pointing radial pattern. But at the exact epicenter of the blast, Kulik found something even more confusing. A stand of trees remained upright, stripped of their branches and bark, but still rooted in place like a forest of telegraph poles. Despite years of deep trenching and magnetic surveys, the expedition found no large fragments of a meteorite, and most importantly, no primary impact crater. This left the first researchers with a massive contradiction. An explosion powerful enough to flatten a forest had somehow spared the trees at its center and left the planet's surface completely intact. The missing hole inspired decades of exotic explanations, ranging from terrestrial volcanic methane outbursts to antimatter annihilation, or even a primordial black hole passing through the Earth's crust. Some researchers pointed to Lake Checo, a deep funnel-shaped body of water nearby, as a possible impact site. However, sediment coriating eventually showed that the lake's deeper layers predate the 1908 event by several centuries. The actual evidence was recovered from local peat bogs. Isotopic analysis of the soil layers revealed a sharp spike in heavy carbon-13 and iridium, elements commonly found in asteroids, locked exactly at the 1908 permafrost boundary. Within these same layers, mineralogists identified grains of shocked quartz. These crystals feature distinct planar fractures that only form under the intense, localized pressure generated by a high-velocity cosmic impactor. The presence of these mineral markers confirms that the event was extraterrestrial. But because they were found on the surface rather than buried in a crater, the explanation for the missing hole had to be sought in the interaction between the object and the air itself. Modern clarity came from physicist Mark Boslow and his team at Sandia National Laboratories, who used 3D supercomputer simulations to re-evaluate the physics of the blast. They identified a flaw in early models that treated Tunguska like a stationary bomb. Those old calculations ignored the massive downward momentum of an asteroid moving at 20 kilometers per second. As a stony asteroid enters the dense lower atmosphere at high speed, it encounters an increasingly solid atmospheric wall. This resistance compresses the rock until it undergoes explosive fragmentation. The asteroid's momentum projects a supersonic jet of vaporized rock downward. Striking vertically, the shockwave strips branches but lacks lateral pressure to topple trunks, leaving them standing. Deflecting outward, it creates horizontal winds that flatten the surrounding forest in a radial pattern. Tunguska showed that a space rock doesn't have to strike the crust to cause regional catastrophe. Its momentum turns the atmosphere itself into a hammer. Tunguska shifted the focus of modern planetary defense strategies. Space agencies now prioritize the threat of low-altitude airbursts, realizing that even objects that don't leave craters can level entire cities. The primary hazard comes from mid-sized near-Earth objects, roughly 20 to 60 meters in diameter. These are small enough to be difficult to spot, yet large enough to cause massive destruction if they enter the atmosphere. Our detection grid is highly efficient tracking large asteroids, but for objects in the 20 to 50 meter range, discovery efficiency drops to 26.8%. This lack of visibility means for an object of Tunguska size, we might only have a 21-day warning before impact. International efforts are underway to close this gap. including the deployment of ESA's multi-optic fly-eye telescope and the start of the 10-year legacy survey at the Vera C. Rubin Observatory in Chile. We have also successfully tested active defense. NASA's DART mission proved that we can kinetically deflect an asteroid, physically altering its orbit by colliding a spacecraft with its surface. The 1908 Siberian blast was a cosmic warning shot. It forced all humanity to look up and motivated us to finally build the tools required to protect the planet.